Good afternoon, everybody. And I want to say that yesterday we had first 15-20 minutes was some issue, and it was not clear. So please accept my apology for that. And let me begin for the today's lecture. Okay. So let me try to recap what we did last class and what concept we are going to be very useful for the coming classes. So what we understood, first we understood the basic block diagram of any closed loop system. Okay. And for that I talk about it that any control system will have a controller D of S, then an actuator, and there is a plant, and there is a feedback element, okay, and there is an output, and this is a input. This is a typical block diagram for any control system. Now we talk about it. This D of S is a transfer function, and this transfer function of these are the individual system. Okay, AS is actuator also. There is input and output. This plant also is in a system. There is input and output. This feedback element also there is an input and output. And this is called negative feedback system because whatever input we are taking it, I am subtracting from the whatever element is coming from the feedback, I am subtracting it here with respect to the reference signal. That's why it's called negative feedback system. Okay. Now this I talk about it, how to represent this thing. That is also I explain you. This is represented by a Laplace transform of a impulse response of the system. Okay, and we have seen this. We can explain it. Okay. Now this thing, since we know that all the systems are linear time invariant system, the entire thing I can write it in one only G of S, like maybe called G prime S. G prime S is nothing as going to be D of S into A of S into G of S. Okay, and this is going to be your feedback element. Okay, and you got the response. This is what we have seen. Now this Ys by Rs, I can write it further, and this Y by R, I am S. Sometimes you see in the literature they omit this S is a free parameter that denotes the Laplace transform, and this I can write it G divided by 1 plus G of H. Okay, this G is nothing else G of S 1 plus G of S H of. Okay, this is what we have done. Now as I mentioned, like our objective in this module which I am talking about it is to find out the response of the system under the influence of different controller. Okay, and for that I mentioned that we have considered this is a simplified block diagram, this G prime HS, and this is the response I have it. So what I will be doing it, I will be analyzing it inverse of Y of S. Okay, and then see how the YT look like. And if you look at it, this Ys is nothing, is going to be Laplace inverse Laplace transform of Y of S. Y of S is going to be R of S, E of S, 1 plus E of S, H of S. Okay, and you take inverse Laplace transform, you are going to get Y of T, that T for more than equal to 0. That's what is our objective, to find out the dynamic response of the system. And this, when I have taken some example and I talk about transient response and steady state response. Okay, when you want to talk about it, so transient, if you want to understand, transient response comes because of the system pole, and this is like as soon as you give some input to the system, whatever response call that we call as a transient response, and as soon as the transient phenomena ends, the steady state phenomena starts. So typically for any typical response, it looks like this. So I would call this is my transient behavior and this is my steady state behavior. Okay. So now we want to understand the how this transient, steady, and entire phenomena is varying with for a control system under the influence of this different controller. Okay. So this is what the recap which I have done it, and also one steady state value, and also which I have explained you have seen. Okay, fine. So now today I will be talking about control system, because what happened whenever we want to analyze the control system, as I mentioned, the transfer function we write in this form. Numerator, there are two polynomials. Maximum power of the denominator polynomial is known as the order of the system. So initially we will restrict our discussion, and that also you have seen in most of the books, they use first order system and second order system for the analysis purpose. Okay, and there are two reasons, because we can analyze mathematically pretty well, and it has been observed that most of the real world system, if you approximate using first order or second order system, your performance are reasonably well. So it's why all of us we do analysis with the first order system and second order system. Okay. So the for example of the first order system which I have explained last class, if you look at it, that I talk about it, there is a, what we call as a first order system. Okay. And in last class I gave an example, there was a load and the load was supposed to move using a torque, and I gave a complete expression, and I am not writing it. You can look back your note, I can see in that there is a input is torque and output is your angular velocity, and this is a system. And if you remember last class I did solve that omega s by T of s is going to be 1 by Js plus B. Okay, that particular system, if you can recall in the previous class, this J is a moment of inertia and B is a viscous friction which we have used it. So here what happened, this is the example which I took it, it was a mechanical system which is giving a first order system. You can also take another example of electrical circuit where you have R and C, the resistor and capacitor, and if you measure output at this end and input is this end, and if you solve it, this is going to be V0s divided by V of Is 1 by RCs plus 1. Okay, that all of you have studied in very fundamental of course in electrical system. Okay, so this my objective is to explain you that your physical system, it could be a mechanical system, electrical system, or hydraulic system. As long as the transfer function is denoted by this 1 by s plus b, you can look at the maximum power is 1 or this, then I call it the first order system. Okay, and initially I want to analyze this, analyze the behavior of the system for the first order system. So since my system could be mechanical, electrical, hydraulic, so we would like to write a generalized transfer function. This is a generalized, like a very general form of writing a transfer function of system. This K is known as a system gain, and tau is known as a time constant. Okay, so this is what we have done. Now, as I mentioned that any control system, when we want to analyze it, we know that in a real world cases the input signal could vary, but here we fix our signal to a specific like unit step or a unit ramp or unit parabolic. So now I want to see how this system is behaving under the influence of unit step input. So you can say, okay, this is my torque, and if it is unit step, so this system which I had mentioned, I am giving input as a unit step function. So you can say I am providing a torque, and that torque exists continuously for so much time. Okay, so now what will be omega t is going to be inverse Laplace transform of T of s divided by tau s plus 1 and k, correct. So now I am not using this Js plus b, you can find out k is going to be 1 by j and tau is going to be j by b. So, here onwards we will leave it that this is a mechanical system or electrical system. I am just talking about it. This is a first order system and there are two parameters involved in that, is k and tau. K is known as system gain, tau known as a time constant. This is what I have written it. This is the first order system. For this there is a k is a system gain and tau is the time constant and input is torque of T of S. Now T of S, as I mentioned, that fine. So this is what we have seen. Now look at, this is going to be inverse Laplace transform of, which is 1 by S k tau S plus 1. Okay, this is what you got it. Now if you solve it, as I mentioned in last class, we will take a partial fraction based approach, and if you do it, this is going to be k 1 by S minus tau S plus 1. You can check it. It comes pretty much well if you look at any book of your mathematics book where they will solve the inverse Laplace transform. And this, if I take an inverse Laplace transform, it's k 1 minus e to the power minus t by tau ut. This is going to be your angular velocity. In this specific case, when you are applying a torque as an input a unit step, this will be response. Okay, fine. Now I want to see that how does it look like when I want to plot it. Okay, so as you can see from this equation, it has a two component k minus k e to the power minus t by tau, and ut, you know that is unit step function given like this on the more than t equal to 0, the positive side. So if you look at it, this response has a two term. Okay, the first term is k, you look at it irrespective of which time, one component is k always fixed. Now look at the second part, k minus t by tau. If you look at it, the typical response goes like this. Oh sorry, it is going to be something like this. Okay, let me use another pen for this. Okay, okay. So this is your second term, this is your first term. Now the overall response is first term minus second term. So if you work it out, it will be something like this. So this is your final response, the way is coming omega t for t, this is the response. Okay, and finally it is reaching to a steady state value. So yesterday, if you remember, I talked about it, steady state value when the, what is the value of this output, in this case is the angular velocity, when t tends to infinity, if you solve it, this will come, you can solve it, it comes as a k. Okay, and another aspect you can look at it, this is the U2 system. As I mentioned yesterday, this will lead to your transient phenomena, and this is because of the input, because tau is this term is because of the system pole. That's why I am calling the due to the system, and this corresponds to your transient phenomena. The other component is because of the input, and I am calling that as a steady state phenomena. Okay, so this initial part will be responsible because of this second term. Okay, that you can see. Now here one more aspect I want to highlight it. All of you might have done whenever you want to plot e to the power minus t by tau. Okay, so this response comes like this, e to the power minus t by 2. I am just plotting a typical how does it look like, and if I plot e to the power minus t by 4. Okay, so if I plot it, it will be like this something. So what I want to highlight it, that the denominator term is a smaller, the decay will be fast. Okay, and here since the 4 is a higher, the decay will be slow. So if you want to understand, if decay is fast in this case, your this approaching towards k will be very, very fast. So here I want to write one statement that if this is the response and I am using two different value of, this is case 1, this is case 2. This is for tau 1 and this is for tau 2. If tau 1 is smaller than tau 2, then I am reaching my steady state value earlier. So what I want to conclude from this, that if your first order system in such a way that this time constant has to be smaller for the system to be fast. Okay, that one has to remember very well. And k is a steady state value. Steady state value. It is not working. It is not playing any role. So in order to understand whether your system is fast or slow, this time constant is going to play a role, and you want this time constant has to be smaller. Okay, this part we have to consider. And this, for first order system, there are two parameters, k and tau are playing a role, that we call as a characteristic of the system. Okay, so what I want, tau has to be as small as possible. And if you want to look at the example of your electrical circuit where I talk about it, your transfer function is 1 by RCS plus 1. So what is the tau there? RC. So RC, the R into C should be as small as possible. Okay, that's what. Now another way to look at it in this case, as I mentioned that your system is k by tau s plus 1. So you know that the system, what is the roots of this? This is the system, and you know the roots of the denominator, the numerator is called zeros of the system, and roots of the numerator is called poles of the system. So look at where the pole is lying, minus 1 by tau. So I can put it 1 by tau. Okay, this is the pole of this system, first order system, and since it's the first order system, is going to have only one pole. Now look at, as I mentioned, tau is small, then system is fast. What does that mean? Tau is small means pole has to be away from the, as far as from this origin. This is my S plane, this is my real part, and this is my imaginary part. So what I want, my, if I want my system has to be very fast, then ideally I should place my pole should be in this as left as possible. Okay, so this is the typical way to understand. Whenever I talk about the first order system, I can say the time constant has to be as small as possible. Another way I can say that pole of the system should be on the extreme of the left side. Then I can say my system is fast. This is what I want. Whenever I am giving some input to the system, system should be quickly responding. And in this case, if you look at it, if this system is quickly responding, I am going to reach the steady state value as soon as possible. Okay, so this part is clear. The what is the property of, what do you mean by, what are the personality of the first order system? There are two terms, k and tau. K is a steady state value, the system gain we talk about it, and tau refers to the time constant. It reflects the a parameter which will tell you whether system is fast or slow. Okay, fine. So this I mentioned the first order system, and which we have seen. Okay, and that these two things we can look at it. Now, so please remember this two term k tau, and you can look at it. If pole is on left side, your system is fast. For the especially for the first order system, example of your second order system. Okay. Okay. As I mentioned, the second order system means the denominator term which I mentioned, the maximum power has to be 2. Okay. So for that, I want to take an example that which we consider for the first order system. This is the load I have. Okay. Okay. And this is the shaft I have made it, and I want to rotate it with a torque T. Okay. And if you look at it, this load, as I mentioned, it is defined by a parameter J. Now, my attribute of interest is not omega, it is theta. Look at, now what I want in my system, the input is torque T, and output what I am measuring is a angular position. And this you might have seen whenever you are working in a robotic concept, what you want, how your robot arm is moving it. So here I am not interested in how far quickly I am going. I am interested in what angle I am moving it. So my attribute of interest is theta. Okay, that's a change. And here, as I mentioned, there is going to be some friction. I am calling as a viscous friction B. Okay, is that part is clear? Now, here one more thing. I am assuming that my shaft is not rigid. Shaft is not rigid means it has a spring constant that I am representing by some k. Please don't forget, don't confuse this k with the previous k which I talked about it, because this spring constant is popularly known as a k, so I am using this term k. Okay, and in a first order system, the k is system gain, so don't get confused. This k is a spring constant. Okay, fine. Now, as I mentioned, what is my system? My system is input is tau and output is my angular movement or theta t. Okay. So, from the fundamental of your force balance equation, I can write this relation j d square theta by dt square plus b d theta by dt plus k theta equal to torque. And this theta is function of time. Please look at it. So this part is clear. This you have studied in your first year of mechanics, where I have a mechanical system, and this is the way work. I can write force balance equation. Okay. Now if I take a Laplace transform, then what will happen? S square j plus Es plus k theta of s equal to T of s. Okay. As I mentioned, if you take a Laplace transform, this is very clear, and and all of you know very well. You can work it out. So now here we look at it. Theta of s divided by torque s is going to be s square k plus b of s plus k. Okay. So you look at it. Here this order is is 2. So this is why we are calling this system as a second order system. Now in this case, this equation which we have got because of the mechanical system, quite possible I may get with a electrical system or hydraulic system. So as long as this power is 2, I call as a second order system. Okay. So as I mentioned that when I am doing a mathematical analysis, I am not looking for that, okay, the system has come from the mechanical system or electrical system or hydraulic system, any system. I am interested in the standard form. So here for any second order system, we use the standard term omega n square s square plus 2 zeta omega n s plus omega n square. Okay. Please note that this is the transfer function of a standard way of writing any second order system. Okay. If you look at it, what will be omega n in this case? Okay, omega n is going to be k by j. Okay, and similarly you can work 2 zeta omega n is going to be this term b by j. So look at, now instead of this spring constant, moment of inertia, viscous friction coefficient, I will be talking in terms of zeta and omega n. This 2 zeta. Sometimes people use this rho also, so I am calling this term as a rho. This is omega n square, and s square plus this one. Correct? This is the way I am writing my standard way of expressing second order system. Okay. So as I mentioned, here onward I will be using this term only. Okay. Okay. One more thing is this omega n is called undamped natural frequency, and this zeta is called, so this part is clear, and this is my, as I go to standard notation, this is my output divided by input. Okay. So this is my standard form of second order system. Omega n is the undamped natural frequency, zeta is called damping factor, and this is the way I am writing it. Okay. Now this denominator, if you look at in literature, is also called characteristic equation. Okay. The characteristic equation, and here if you know this is a second order system, so there are going to be 2 poles, as I mentioned, there are 2 poles because there are 2 roots exist. Okay. And if you solve it, the 2 roots S1 and S2 is minus zeta omega n plus minus omega n 1 minus zeta square. Okay. Is it visible properly? Okay. Fine. So what I have written, I am finding out the roots of this equation. There are going to be 2 roots, S1 and S2, and they are going to be complex conjugate. And if I plot it in a two-dimensional case, the location is going to be this. Real axis is going to be zeta omega n, and imaginary axis is going to be omega n 1 minus zeta square. Okay, and this quantity is also sometimes referred as a omega d for damped natural frequency. Okay, omega d is called damped natural frequency. So this what we understood. I have a second order system. The second order system, I just wrote it a basic differential equation. I took a Laplace transform, and after Laplace transform, I am writing in a standard form, and I have defined some term. Omega n is the undamped natural frequency, zeta is the damping factor, and the roots of this we can solve it is going to be two term. Look at this conjugate location. Real part is zeta omega n, and imaginary part is this term. This we call the damped natural frequency. I will explain you why I am calling a damped natural frequency and undamped natural frequency in a short while. Okay, fine. Okay. So fine. So as I mentioned, this is going to be your. So let me write it ys divided by rs is going to be omega n square s square plus 2 zeta omega ns plus omega n square. Okay. So you can say whenever we talk about a system, you can talk about the second order system is represented by this term zeta and omega n, and I can call as a personality of the system. Correct? Okay. So as I mentioned, our objective is to analyze y of t greater than or equal to 0 for any arbitrary input. Okay. Now as I mentioned, when we want to do analysis, we go for a standard input signal, how your system is behaving for a standard input signal, and then leave to the system how it behaves in the real world scenario. Okay. So I will be looking for y of s inverse of Laplace transform of rs omega n square s square plus 2 zeta omega ns omega n square. Okay. Now initially I am taking as I mentioned that I talk about it, 3 standard input signal: unit impulse, unit step, unit ramp, and unit parabolic. Okay. So let me understand with the unit step input. Okay. Because once you know the unit step, how does it behave? Unit ramp also it behaves similarly, and parabolic also we look at it we can extrapolate it. So very much I am going to analyze with respect to unit step and unit ramp only. So in that case, what will happen? R of s is going to be 1 by s. All of us know the Laplace transform of unit step function ut is this. Okay. So your yt is going to be inverse Laplace transform of omega n square s square plus 2 zeta omega ns plus omega n square. Okay, fine. Okay, this video got it. Now you have to take a inverse Laplace transform and solve this entirely. Okay, so before fine. Okay, so okay, so here this to finding out the inverse Laplace transform, I am using the term directly because I don't want to spend time on solving this mathematical equation. It is a standard thing. It is given in the M. Gopal book and several other books. So I am just writing it. This y of t directly is going to be. I am just writing a term because my objective is to explain you the meaning of the term. So this is going to be response of a second order system for a unit step input. Please, this part you can look at it in any book, M. Gopal, Nagarath M. Gopal book. You can find out. I am not going for the derivation of this thing. It is not so difficult. If you know the how to find the inverse Laplace transform, you can get it. Okay, because our objective is to understand how it is behaving. Okay. One more aspect that, as I mentioned last time, you also go for steady state value, that limit t tend to infinity yt at a steady state value, and this from the final value theorem, what we know that what we find out, this is equivalent to limit s tend to 0 find out, and what it will come, If you work it out here, this will come, yt will tend to 1. So, in this case, if you take a second order system, you are getting a steady state value 1. So, you are reaching a ultimately steady state value. Okay. So, we have to understand this term. For that, I wanted to explain. So, here as I mentioned, the terms are involved, zeta, omega n and all these things. So, I will tell you that when we analyze it, the analysis we consider 3 conditions. First, when zeta equal to 0. Second, zeta is greater than 1. And third, okay, these 3 conditions. So, we want to understand this behavior by t, and we have seen this entire term comes. So, I want to consider what this term behave for 3 different conditions, 3 conditions, correct? Huh? Okay. Now, consider a case when zeta equal to 0, okay. So, plug in, when zeta equal to 0, what will happen? Yt is going to be 1 minus, this term will be 0, this term will 1, so it's going to be sine omega n t only. And if you solve it, zeta equal to 0, something by 0 is infinity, so pi by 2, okay. And if you work it out, it is going to be 1 minus cos of omega n t, okay. Okay. So, if you plot it, how does it look like? It will look like something this, because it's some sinusoids. So, I can look at it, my response is going to be something like this. It's a sinusoid and the frequency of the sinusoid is governed by this omega n, and this omega n I am calling as a undamped natural frequency, okay. That is why you can see omega n t, sin omega t, you know, sin omega t plus phi, this term is a phi, is a phase. So, when zeta equal to 0, this system is oscillating. So, here as I mentioned, irrespective of your mechanical system, electrical system, what we want to say, if you have a second order system, your zeta is 0, it means your response is going to be oscillatory. So, here one has to be careful. Am I looking for response of a system to be oscillatory? Does it require some system? It depends on the application. Now, think about it, a case you are controlling a movement of an robotic arm. Now, if it is a second order system and it so happen you have chosen zeta equal to 0 because of some ambient constant, and now give the input, it will vibrate like this, correct, oscillatory. It will go up minus, up down, up down. Is it required? It is not required. Quite possible in some scenario it might require. So, that is why this zeta equal to 0 is not at all a desirable things in when you are using second order system, okay, fine. Now, let us think, this is a zeta equal to 0, we say oscillatory behavior, okay. Now, when we want to understand this, first let me understand this part and it will be clear what happened is zeta is this part, zeta I am calling this, please note that this terminology is my zeta, e to the power minus zeta omega and t. Some of you might use rho term, so I am sticking the term zeta, okay. So, this if you take it between 0 and 1, understand this part, okay. Look at this term is 1 minus this term sine of omega t plus phi. Is it clear to everybody? What I am saying, this term is sine omega t plus phi, okay. So, all of us know this term is some sine omega t added by some offset this phi, because this is not function of t, okay. And this you know e to the power minus zeta omega and t, okay, and this is some constant. So, you know the exponential function will be coming down, okay. So, what I can say, so if I look at it is, okay, this is 1 plus e to the power minus zeta omega and t 1 minus zeta square. Since this sinusoid can go plus and minus, so I am writing this as a envelope is going to like this, okay. this is going to be 1 minus e to the power minus omega n t 1 minus zeta square. So what will happen? Your response of the system, because this is the envelope and the sinusoid is coming, so your system response will be something like this. Okay, this part is clear to all of you, that this is like I am trying to explain you, when you use zeta between 0 and 1, this is the phenomena come. Okay, so I can say that my response of the system, you look at, it is a damped sinusoid, correct? It was a sinusoid, it started and now it is getting damped out and it is coming here. Okay, so this is the going to be response of the system or a second order system. If you give this input, it will come. Now here, as I mentioned last just now, this we are calling omega d. Omega d is nothing, omega n 1 minus zeta square. So look at this, damp is coming with a sinusoidal frequency of this omega d, omega n into 1 minus zeta square. That is why it's called damped natural frequency. Damped natural frequency. Okay. Now you can understand the difference. Omega n, omega is undamped natural frequency, this oscillation. And when I am using this zeta some specific range between 0 and 1, it is going to be like this, damped natural frequency. Okay. This is going to be, so this if you plot it, if you have some MATLAB or any plotting box, you can see you plot it, if you choose between 0 and 1, this is going to be typical behavior. Okay. Okay. Now consider the scenario when zeta is exactly 1. Okay. When if you plot it, the response is going to come like something like this. Okay. And if we keep on increasing zeta, it will be like this. So this is where if you increase zeta more than n, the response of the system, this is yt with respect to t, and this is where it will come. So okay, so all of you look at it, I am plotting yt versus t. In this case also I am plotting yt versus t. Okay. So if you look at it here, when zeta is more than 1, this behavior is going to like, there is no oscillation, and this scenario is called over damped scenario. Means your oscillation has been removed. Now if you plot it, if you take zeta more than 1, the response is going to be like this. There is no oscillation, and that's why it is called over damped scenario. Okay. And if you take a zeta equal to 1, this is the scenario when oscillation has just disappeared. If you solve it, you can look at it, the oscillation is just disappeared, and this is called critically damped scenario. Okay, this is called critically damped scenario. Okay, fine. So now I want to summarize it. This is the response of a second order system. It's a typical second order system. It could be mechanical system, it could be electrical system, and I want to see how does it look like. So there are some variable and I am plotting it. Okay. So first case I took it zeta equal to 0. It means it is going to be oscillatory, and as I mentioned, it is not desirable in any control system or any system your output is oscillating. Correct. And this is the over damped scenario. This is also not required, because if you keep on increasing it, this response will take lot of time to reach the steady state value 1. Correct. As I mentioned, it will take lot of time, and this will make your system slow or either say sluggish. So that is also not a desirable situation. I don't want my zeta should be 0 and more than 1, because this will make my system sluggish or slow, and this will make my system oscillatory. So only thing it is required, the system when I am the system which I am using it, the zeta should be between 0 and 1. Okay, so that I can get this response, and I will look at it. This is a desirable scenario. Okay. So as I mentioned in the case of the first order system, that your time constant has to be smaller and smaller to make your system fast. How do I say the same thing here? Okay. When I am saying what is desirable, should I use zeta equal to 0.2, 0.3, 0.5? It will be keep on going. As I mentioned, zeta is two range, 0 and 1 is desirable. Beyond 0 is desirable, Beyond 1 is not desirable. It is desirable between these two. So, what is the optimal value? Okay. For that, we will be quantifying this behavior using some parameter. Okay. And those terms I am going to write now. Okay. Fine. Okay. So, this part is clear, zeta equal to 0 more than 1. Now, I just wanted to highlight one more thing here is that if you remember, there is a denominator term. What was the denominator term? It's s square plus 2 zeta omega n s plus omega n square. Correct? And what I just has explained, the roots of this system is s1 and s2 is minus zeta omega n plus minus omega n 1 minus zeta square. Now you remember this term, damped natural frequency omega d. Okay. So this is the roots of the system. Now if we look at it, this is my S plane, and what will be the location of the roots of the system? This is going to be real part, okay, and the real part is going to be denoted by this part, zeta omega n, and this imaginary part is omega n 1 minus zeta square. Okay, this is going to be a typical scenario. Okay, this second order system which has a two poles, they are in a conjugate location, and the conjugate location, the real part is minus the zeta omega n, and imaginary part is omega n root of 1 minus zeta square. Okay, fine. Now think of the scenario when zeta equal to 0. When zeta is 0, real component is going to be 0 and imaginary component will be here. So in that case, your this is zeta equal to 0. When you take a zeta equal to 0, the two pole location is going to be here. Okay. Now you take a consider when zeta is equal to 1. If you take a zeta equal to 1, this term will be 0 and this term is going to be omega n. So somewhere here you can call it the two poles will be lying. Okay. So what I want to highlight it, if you increase from zeta equal to 0 to 1, these two poles start traveling it this manner. If you take slightly up, this two pole location will be here, slightly increase, two poles will come here, again increase, two poles will come here, two poles will come here. So that's the movement of the pole. So what I wanted to say that till now you talk about in zeta, now I can talk about it, the movement of the pole location. If the two poles are lying here, it means it is a oscillatory behavior. If the two poles are lying on the real axis, this is a critically damped scenario. And if you keep on doing it, it will come. But I am interested in putting my zeta in such a way that pole should be lying in between as a desirable. And if you draw it, you can write it, and this phi comes cos inverse of zeta. You can solve it, correct? This is going to be base, this is going to be a perpendicular. So tan theta is going to be this divided by this, and if you solve it, this theta, you can look at it. Okay. So this part I wanted to emphasize it by looking at the pole location. I can say what is desirable. Okay. This is not desirable, this is not desirable. The desirable is in between these two. These three conditions which we have talked about it. Now, okay. So this we are studying the response of a second order system for a unit step input, and as I mentioned, I am choosing between 0 and 1. Okay. The typical behavior will look like this. Okay. Finally, as you go t tend to infinity, it will reach to 1. Okay. And as I mentioned that this phenomena, as well as its speed, it is going to a steady state behavior. Okay. So I want to define some quantitative value to judge that what should be my good value of zeta and omega n, so that I can say my system is fast, slow or something. As I mentioned in the first order case, my pole has to be completely left side, that I talk about it, correct? So for that there are few parameter has been defined. One is known as a rise time, peak time. I will explain each one by one. Maximum peak overshoot and settling time. Okay. These are the few things has been defined in the literature that these 4 parameters will be defining it. Okay. So what it says? Rise time. Okay. Rise time is the time, okay, time required for this value to reach from 0 to 100%. That is called rise time. What is the time required for this response to reach 1? Okay. And if your system is overdamped, as I mentioned, it so happen in some case you might have used zeta is very more than very less than 1, very larger than 1, then I come to the overdamp scenario. In this case, they measure what is the time required to reach the value from 10% to 90%. Okay, this is the rise time. Peak time. Peak time is the time required to reach this peak in the response. So I can say at what time I am reaching the first maximum. This is known as the peak time. So I have written peak time. Maximum overshoot. Maximum overshoot is about this. Okay. How much I am overshooting with respect to steady state value. You see this? This is called maximum overshoot. Okay. So the maximum overshoot also is defined. I mean, we will look at the quantitatively. I am just explaining first subjectively. So please look at it. Maximum overshoot is about this. Okay. Settling time. It's a very important parameter that we use it. It says that okay, what happened if you look at it, this is some kind of oscillatory behavior, and as there is a response comes, it will be a sinusoid, and as you keep on going it, this oscillation will decay. But as we seen that at t tend to infinity, this value goes to 1, that is very much sure. But still, before any input, it is going to t tend to infinity, whatever way. I am much more greedy to know about it. Can I quantify something that this, how quickly I am reaching to this value? Okay. So for that, what happened depends at what time, because this is going to be oscillatory. So at what time I am reaching in this zone? Okay, I can use this black marker. At what time I have reached into this zone of this 2% tolerance, let me call as a some 2% value of steady, mean like 1 to 2% plus 2% minus. So at what time I am reaching this bandwidth such that I am not coming out? Let me clarify. Again, let me speak that I am talking about at the time which this response will be going in a bandwidth so that it won't come out again from this 2% tolerance band. That's what is required. Okay, is that part is clear? That I am interested in finding out the at what location, at what time my response will reach towards this tolerance band in such a way that this will not come out. I can't say this as my settling time, because here onward I am going up, I am going down, but here onward I won't come. So that is what is called settling time. Okay, fine. So this term now we will find out quantitatively. Okay, so rise time. So rise time is the time you require to reach this value 1. So it does, what does that mean? This yt r is going to be 1. Okay, because this is the response. Now you solve it. This is will lead to e to the power of minus zeta omega n t 1 minus zeta square sine of omega n 1 minus zeta square t plus tan inverse 1 minus zeta square theta. Okay, this will lead to a 0. Just because this 1 will get cancelled out, this term will lead to a 0. And if you solve it, which I am not doing it, this will lead to rise time is T of R phi minus tan inverse 1 minus zeta square by zeta divided by omega n 1 minus zeta. Okay. So, I am skipping two terms here. Please note that I am not solving the entire part. This is the response, and I define the rise time, the time at which the response becomes 1 first time. So, this ytr equal to 1, you plug it here. So, this term will be left out, it will be equal to 0, and if you solve it, this will lead. So, this is called your rise time. Okay. You can look at it, it's a very standard derivation, it is given in the book, especially if you look at M. Gopal book, it is given there. So, I am just using, this is the mathematical equation to find out the rise time. You can look at the rise time zeta, and you can look at it is inversely proportional to this part. Okay. So, this zeta, if you look at it, is if the zeta is smaller, rise time is going to be smaller. Okay. And you can look at it, if zeta is 0, what is the typical response it comes? It is going to be sinusoid. If the sinusoid, you will reach this one value very quickly. It makes sense. Okay. This rise time is clear. Okay. Please note down, this is the relation of the rise time. I am writing it here, phi minus tan inverse 1 minus zeta square divided by zeta divided by omega n 1 minus zeta square. It is written in my handout also. You can look at this relation, okay, which I have provided in the this one. Okay. Next is peak time. Okay. So as I mentioned, let me draw it again. This part. Okay. Same thing. I am just drawing it. This is a typical behavior. So this is the time I want to know. At what time I am reaching this peak. So I know how we know from the fundamental of a differential equation that when this equation, this entire response is going to reach a maxima. So what we do? We differentiate it d by dt y of t equal to 0. Correct? We want to know at what location it is reaching a maxima. I mean, maxima is going to be a saturation point. The derivative is going to be 0. This point also is going to be 0. This point also 0. But I am interested only this part. So if you work it out, if you differentiate this dy dt of yt equal to 0, and whatever response comes, if you solve it, I will get a peak time. Okay. So again, I am telling you this derivative and all this is a very straightforward. All of you can do very simply. All of you are good at mathematics. So I am just writing the direct term, and this will give me a peak time is going to be, this relation comes. I am just writing it. This is my peak time. Tp is going to be omega n into 1 by root of 1 minus zeta square equal to n pi. N is a some constant, it will vary 1, 2, 3, 4. Okay, if you take n equal to 1, this is going to be a first maxima. If you take n equal to 2, it is going to be second minima, third minima, this first maxima, second maxima, this first minima, second minima. So it will be keep on going it. So when I am differentiating it, this term, this response will be 0 at several locations, correct? But I have to choose a location where it is becoming maxima first time. Okay, so that's why I am choosing n equal to 1, and I will write it directly. This is my peak time, and peak time is Tp omega n 1 minus zeta square. Okay, this is the peak time. Tp equal to 5 divided by omega n 1 minus zeta. Okay, fine. So this is my peak time, the second term which I am using it, and I wanted to write it here. 5 divided by omega n 1 minus zeta square. This is peak time. Now the second, third, correct? Rise time is clear. Peak time we got quantitatively. Now maximum peak overshoot. The maximum peak overshoot is this quantity. Okay, and the way it has been defined is this relation. It is peak overshoot MP is defined as a YTP minus 1 divided by y of infinite into 100%. Correct? What does this mean? What is the value y of at peak time is this minus y of infinity, that what is the steady state value I am reaching it here, divided by y infinity. So it is like I am trying to find out how much I am overshooting with respect to this steady state value. This is what it means, ytp minus y infinite divided by y infinite, and this I am writing in terms of the 100, in terms of the percentage, and this is known as the maximum overshoot, MP. Okay, this part is clear. Maximum overshoot, again if you solve this entire thing, you plug it, and this final relation I am writing it, it is going to be 100 into e to the power minus pi zeta 1 minus zeta square. Okay, please note that this is pi zeta divided by 1 minus root of 1 minus zeta square. Okay, this again I am not writing it, it's pretty straightforward, you can solve it. Okay, so the third part which I got it, maximum overshoot is defined by this. Okay, and if you look at it, when zeta equal to 0, this term is going to be 1. So what happens? Overshoot will be maximum, and if you remember, you don't want maximum overshoot to go at very high value. Correct? What it will do? Quite possible it might, your response is going to be unusually very high value and will spoil your system. Another part, you don't want oscillatory behavior. Okay, so this part is clear. Now the very important term is settling time. Okay, which I want to take it. So settling time. Settling time, to explain this, let me use this term, this plot. Okay. Settling time is, as I define you, try to understand that I will define a tolerance band. The tolerance band generally typically defined 2%, 5%, it is well known. So here I will be interested in finding out time when I am reaching this point. Okay, this is a response yt with respect to t. So I am interested in the location at the time at which I will enter a tolerance band and I will not come out. That I want to say settling time. So what it means is that I know my steady state value is going to reach 1, but it will be at very long time, t tend to infinity we say. I am not so much interested in that what will happen, the steady state value is 1 at very long time. I am interested. So sometime what happened, we re-look at it, okay, it doesn't matter, my response as long as is reaching to some tolerance of the steady state value, I am happy. Like you want my steady state value to reach 0.9, okay, oh sorry 1. If you are reaching a value of 0.98 and 1.02, it is acceptable to me. It depends on the application to application, but there are some application I say I am interested in reaching to a steady state value, not only to the exact value, but within tolerance I don't mind. That is where the settling time plays a role. So I am interested in finding out this time. Okay, this part is clear. Okay. Now very beautiful phenomena I wanted to explain here is this. This is what I have mentioned. Now you are choosing zeta between 0 and 1. So you will get something like this. Okay, and let me call MT1. Okay, this is my settling time. Okay. Now what I will be doing it, just if I reduce my zeta, so the next response, let me it is going to be something like this. It's a typical behavior. So now if I reduce my zeta, this is my time t2, correct? So when I have reduced the zeta, means zeta I know 0 to 1. Now I am talking about the value less than 1, and let me call that time is settling time. Okay, T1, TS1 I want to call it. Now what I did it, I reduced my zeta further, 0.9 to 0.7. So there is a good chance I know oscillation is going to be there. So I will be reaching my band early, PS2. Now if I reduce it further, 0.9 to 0.7 and 0.665. So again if I look at it, I am going to reach something like this. So here what will happen? The settling time TS1 will be less than TS2, TS3, correct? What is desirable? This settling time, because I am entering the tolerance band very quickly, and that was is desirable. Okay. So what I want my settling time to be as small as possible. So as I mentioned, I kept reducing from zeta equal to 0.9 to 0.7. I enter the tolerance band earlier, that is desirable. Now I reduce it further, desirable. Do you think that if I keep on reducing, I will reach the same? No. Why? If I reduce it further, then what will happen? The behavior will be something like this. It will go like this, and yes, exactly. So what happens if I reduce further from zeta 0.5 to 0.4? Then my oscillation will be big and I will reach my tolerance band pretty late. So this will be some TS4. So this is what I want to emphasize, that if you keep decreasing zeta from 0.9, 0.8, 0.7, you will be reducing the settling time, but there will be some location where zeta will be such a way that you will get maximum oscillation and settling time will be increased. Okay, that's a very, very important concept that one has to understand. So this part is clear. What I am saying, the settling time. I use some zeta equal to same thing, analyze it, I saw that it is reaching to the band earlier. I reduce my zeta, the damping factor further, I saw that it is reaching much earlier the band. Then I reduce it much further, I got it, the settling time is further reduced. But if I reduce next level also, then what I observed, because of this oscillation behavior, I will be coming out from the tolerance band and I will be reaching my tolerance band very late. So my settling time has increased, which is not desirable. So what people have observed, this is a typical one plot which we have got it, and if you look at it in M Gopal, you can see that this is a settling time, omega and TS I am saying, because omega n is a normalized settling time. So if I increase zeta from 1 to this for some tolerance band, it will come down. Now if you reduce it further, it will go up. Okay, if I reduce it further, it will go up. So this is what I have explained you, correct? If I look at it, settling time, what was 1, and if I keep reducing in zeta, this is my zeta, this x-axis, and this is omega and TS, the settling time is coming down, but I have reached to some stage, somewhere 0.4 or something, I have gone further up, then I will keep on going up. So here we want to conclude that if you are reducing zeta, if you keep on reducing it, it is not going to serve your purpose. Don't think that I am making my system fast. Settling time is small, means system is fast. You are reaching a band earlier. Okay, so that cannot hold true that you keep decreasing zeta and you will be happy. When it's coming, you can understand because of oscillation behavior. Okay, this part is clear. That rise time, peak time, overshoot, settling time. Rise time I want small, but if you keep it is inversely proportional to zeta, it means if you make a zeta equal to 0, my rise time will be very small, but that is not desirable, because there won't be settling, the response will not settle down. Okay, maximum overshoot should not be very high. Okay, because if it is very high, it will be very high, and it might spoil some of your, because output is going to be very high, it might spoil your next component. Okay, so this is what this 4 metric which I have explained you. This is rise time, peak time, overshoot, and settling time. Now how do I define this settling time? Quantitatively. So for that, what has been observed, that since I know this decay is happening because of 1 minus e to the power minus zeta omega and Ts. So this is coming, this term, if you look at it, this is 1 minus zeta square, correct? This is the exponential term is coming. So I want to see at what time it is reaching to a tolerance band. Okay, so I can write this response this manner, that at what time 1 minus e to the power minus zeta omega n Ts 1 minus zeta square is reaching to a 2% tolerance band. So since I am taking with respect to 1, this is going to be 1.2. Okay, this is going to be 1.2. So 1 will get cancelled out. I am writing a 0.2. Okay, and if you solve it, so it has been observed that zeta between 0.4 to 0.7 is desirable in most of the cases. And if you work it out, this is going to be zeta omega n Ts log of 0.2 1 minus zeta square. And if you find out the range of value, like if you take a zeta equal to 0.4, this comes around 3.9. If you take zeta equal to 0.7, it comes from 4.3. Okay, this two value. Like for this, I know that typically in most of the practical system, the zeta is desirable between 0.4 and 0.7, and I am finding out this quantity at 0.4. If you compute, it's going to be 3.9. At 0.7, it's going to be 4.3. So it has been written that it takes this as 4. So now zeta omega n Ts. So your settling time is 4 by zeta omega n. This is the quantity we use it when we want to say what is the settling time this derivation has come. So all of you are clear how this settling time 4 by zeta omega n has come, because of this assumption that I am using zeta damping factor between 0.4 to 0.9. Okay, fine. So all this is clear too. Okay, so please note down this equation. What is rise time? This equation. Peak time also you know. Maximum peak overshoot also you are aware of. And settling time is 4 by zeta omega n. How it has come? Now we can see. Okay, fine. So, and this is also like, let me explain you. This is a typical behavior of a second order system. So what you want, if you keep decreasing zeta, this will be a oscillatory behavior, correct? This is going to be your oscillatory behavior, and the oscillatory behavior though, sorry, please I am going. So if I use very small value, this is going to be oscillatory behavior. So my rise time is very small, but it is due to the oscillatory behavior, it will not reach to a steady state value. It will not reach to a steady settling time. That's why it is not desirable. Now if you go for further increase zeta, you will get the behavior something like this. Okay, and that is a desirable. And here also if you may keep increasing zeta and zeta is more than 1, it is going to be an overdamped scenario. It will take lot of time to reach the steady state. This part is clear, that when we are working on a second order system, what is the best value of zeta? As we know, I can't choose more than zeta equal to 1, because the overdamped scenario, it will take lot of time to reach the steady state value. On the other hand, if you take a very small value, it is going to be oscillatory behavior. I have to be in between, and for that there are 4 terms which we have defined: rise time, peak time, overshoot, and settling time. I want settling time to be as small as possible, overshoot be as small as possible, peak time should be as small as possible, and rise time. So this is a system given to you. This is called unity feedback system. Means here feedback is unity. Please, I would say that I am not spending time. What is the unity feedback system? This is a mathematical way of representing. It doesn't mean that transfer function, it is not necessary that your transfer function has a unit value, okay, of the feedback element. So you can go back and look at what is the unity feedback system. I am assuming it that all of you know, and this is what I have talked about it, because my focus is to understand the time response analysis of a control system. So that's why I am not sticking what is the unity feedback system. This is the system is a unity feedback system for which the transfer function on the forward path, this GS is given to this RS and YS. Okay. Now your objective is to, what is the settling time, peak overshoot from the road. So what you will do it, you will find out YS divided by RS is going to be, this is you know, G of S divided by 1 of GS into HS. So this is going to be 16 divided by S square plus 1.6S is going to be 1 plus 16 s square plus 1 point. Is that part is clear? This is GS. 1 plus GS into HS is going to be 1. If you solve it, it's going to be 16 divided by s square plus 1.6s plus 16. Okay. So this system has a entire transfer function is this. This is your numerator and this is your denominator. Now this, you know, that is a second order system. So you have to compare with the standard form. And what is the standard form? S square plus 2 zeta omega ns plus omega n square. Correct? And if you compare these two equations, what will happen? Omega n square is going to be 16. Okay? And 2 zeta omega n is going to be 1.6. Okay? So omega n is 4, and if you solve it, zeta is going to be 1.6 divided by 8. Correct? 4 into 2, 8. 1.6 divided by 8, and if you solve it, this is going to be 16 by 80. Okay? So you got zeta and omega n. Now you find out settling time and peak time. So peak time, you know, let us start with the settling time. 4 by zeta omega n. So 4 by zeta omega n is going to be nothing else, 4 by 1.6 into 2. This is going to be settling time. Similarly, I can find out the peak time, and the peak time which I have computed, it comes, zeta comes as a 0.2. I am writing it the value which I got it, and peak time comes to a 0.8 seconds. You can solve it if you have a calculator. This is the numerical value, and you can find out the maximum peak overshoot. Okay, the maximum peak overshoot is going to be something e to the power minus pi zeta 1 minus zeta square. Okay, and this, if you solve it, I have got the value 52.6%. Okay, what I have got 52.6%. Is that clear? This is a numerical way of solving. I have a unity feedback control system. This is a negative control system, and then I got it. I solved this transfer function. Then I compared with the standard equation. This is a second order system, so I know it's going to be undamped natural frequency. Then I have to find out the damping factor. With this parameter, I can find out settling time, peak time, maximum overshoot. All these equation are their formula is now we have derived it. Okay, and you can understand the meaning of fine. So this is just I took an example so that if you have some control unity, if you have a control system and a second order system, you can find out this quantity: settling time, peak time, rise time, maximum overshoot, and you can understand. You can give the logical reason what it is a desirable value. Now we slightly I want to summarize this little bit. What we discussed till now: first order system, second order system. Standard term is k by tau s plus 1, and this is omega n square s square plus 2 zeta omega ns plus omega n square. Here tau should be as small as possible, and k should be closer to unity. That's a desirable. And here this zeta should be 0 and 1, and this oscillation frequency, it depends on the what we are using it. So mostly we define some quantity: settling time, peak time, rise time, on overshoot, and this all we can look at it. So this what this module was to understand the response of a system which are defined using a first order relation, second order relation, and this quantity we have used it, and this quantity we are going to use extensively when we are going to study the behavior of system under the influence of different controller. Okay. Now one more part I wanted to explain here is the steady state error. Okay. Okay, this is a steady state error. So what does that mean? That R of S Okay. So as I mentioned earlier also, this is going to be a typical block diagram of a control system, closed loop control system, correct? This is going to be a plant, this is going to be H of S, and I am just mixing it all your controller, actuator, everything in one. Okay. So as I mentioned, the steady state value, how do we define steady state value? Is limit t tend to infinity yt, that we say steady state value. Now there is another parameter which has been defined called steady state error. So for that, this is the input signal and this is the feedback signal, and let me call this is the error signal. So what I want in a control system, that whatever input signal is given to here and whatever my feedback signal, the error between should be as minimum as possible, correct? If you have minimized the error, your control system is working very much fine. Now take the example of controlling the temperature of a room. So the reference temperature is suppose 25 degrees centigrade and your actual temperature is suppose 23. The difference is going to be 25 minus 23 is going to be 2. So that is the error. Now what you want? You want to give the input in such a way that reduce the voltage or whatever the flow of the steam in the room, so that the difference should be 24 minus 24.9 something. Okay. So what you want, this error should be as small as possible. Okay. So for that I can write it E of S is going to be R of S minus H of S into Y of S. Is that clear? What I want at this point, the signal will come HS, this is YS into HS will come here, and this ES is going to be RS minus HS into YS. Okay. Now divide this equation by RS. Okay, so this is going to be 1 minus H of S, Y of S, RS. Okay. Now what is this? Y by R is your transfer function. So I can write this in a form equal to 1 minus H of S, E of S, 1 plus E of S, H of S. Okay. If you solve it, this term will get cancelled out. I am going to get 1 by 1 plus E of S, H of S. Okay. So this is going to be E of S, R of S. Okay. I'm sorry I'm using this different color of pen because it is getting dried up, but I want to convey. I hope it should not be a problem. Okay. So this is what we got, E of S divided by R of S. Okay. So what I want, this steady state error ES should be as small as possible. So I have to see when S tends to 0, S of ES, correct? Another way, limit E tend to infinity E of t, correct? What I want at steady state value, your error should be close to 0. So using final value theorem, I have written the steady state error as a limit S tend to 0, S of ES. Okay. So now if you look at it, it is going to be something limit S tend to 0, S, ES is what? I can got it from here, RS 1 plus E of S, H of S. So this is what I am going to analyze it. Steady state error, correct? Till now I was talking about the steady state value. Now I have moved to a steady state error. Steady state error is given by this relation. Okay. Now we will see how this steady state error act for different kind of input. Okay. So this diagram is clear to all of you. Now if I take my input as a unit step input. Okay. If I take my unit step input, then what will happen? Input is going to be RS is going to be 1 by S, correct? In that case, your steady state error is going to be limit S tend to 0, S, this is 1 by S, 1 plus E of S, H of S, okay? So this S will get cancelled out, okay? This S will get cancelled out, and this is going to be limit S tend to 0, 1 by 1 plus E of S, H of S. And if you look at it, this, let me define a term Kp limit s tend to 0 g of s hs. Okay, okay, and this quantity, this error is going to be 1 by 1 plus p. Okay, this, so if I have some system for which I am giving a unit step as an input, my error is going to be 1 by 1 plus Kp, and Kp is known as a position error constant. Okay, is defined position error constant. Okay, later it will be clear. It has been used the terminology. Now, if you take a input as a unit ramp, so my Laplace transform of unit ramp is going to be 1 by s square. So, what will happen now in this case? Limit s tend to 0, s divided by s square 1 plus g of s hs. Okay, this part is clear. So, now your s will get cancelled out. I know limit s tend to 0. The first time I also this s will get cancelled out. S will be there. So 1 by s g of s hs. Okay. Now, let me define a term that's called Kv limit s tend to 0 s g of s hs. Okay. So, this error is going to be 1 divided by k of v, and v is known as the velocity error constant. Okay. So, you can look at it, if it's a position, if you put s, it is equivalent to giving a derivative. That's why you can, from the position, it has become a velocity. Now, consider the input if it's a unit parabolic, correct? So, unit parabolic, the r of s is going to be 1 by s cube. Okay. So, in this case, what happened? Again, if you solve it, limit s tend to 0, s divided by s cube 1 plus g of s hs. Okay. And if you write it further, it is going to be something like 1 divided by k of a, where k of a is going to be limit s tend to 0 s square g of s h of s. Okay. So, this is known as the acceleration error constant, correct? So, this is what you got it. I am defining a steady state error. This is the equation. Now, I want to understand the behavior. If my input is unit step, my error is going to be 1 by 1 plus Kp, and this Kp I can evaluate by this. If my error, if my input is a unit ramp, my error is going to be 1 by Kv, and this is going to be limit s GHS. If my input is going to be 1 by s cube, my error is going to be 1 by Ka, and K is an acceleration error constant. So, these three terms I want you to remember. This is the position error, the velocity error, and as an acceleration error. Okay, and this has a meaning I want to explain you. So, here I am just writing it. Your Kp is limit s tend to 0, g of s, h of s. Okay. Kv is limit s tend to 0, s g of s, hs, and Ka is defined as limit s tend to 0, s square, g of s, hs. This is a position error constant, velocity error constant, acceleration error constant. And if I know these things, I can find out the response of I can find out the error for this any input. Okay. Now here I want to define one more term here, that is Gs into Hs we have come across. It is also defined as the open loop gain. Okay. So this open loop gain, it is going to be some polynomial. Open loop, this is also called open loop transfer function. Okay. It's called open loop transfer function. Okay. And this again I can write it some two polynomial, numerator divided by some denominator, and if I write it numerator divided by denominator, then okay, I can write it k s minus z I, and s to the power of p s minus ej, j varies from 1 to n to n. Correct? This I can write it. This is the one polynomial which has a numerator term, denominator term. Numerator term I am writing as a multiplication of several roots. Denominator also I am writing it. There is a one term coming s to the power of p. Okay, this p denotes the type of the system. Okay, p denotes the type of the system. Okay, so the type of system, if say p equal to 0, we say type 0 system, p equal to 1, type 1 system, p equal to 2, type 2 system. In general, I can write a type n system. I want to emphasize one point, that this type system is different from the order of the system. Okay, so don't get confused that order of the system is equal to type of the system. No, order of the system is something different and type of the system is something different. Okay. Now, I want to say that type 0 system, type 1 system, type 2 system, and if you give this type of system unit step as an input, unit ramp as an input, and unit parabolic, correct? Okay. If my g into h is a type 0 system, means p equal to 0, in that can what happen? Limit s tend to 0, this error is going to be 1 by 1 plus kp. Is that clear? And kp is limit s tend to 0, g0 as 0. There will be some finite quantity. Now, go for type 1 system. In type 1 system, what will happen? This is going to be 1 by s some quantity. Now, as s tend to 0, this quantity is going to be what? Infinite. Okay. This kp term is going to be 0. Sorry, kp is going to be infinite. Okay. So, in this case, the 1 by infinite error is going to be 0. Now, if type 2 system, again this term is going to be 1 by s square, s tend to 0, this kp is going to be infinite, 1 by infinite is going to be 0. What I want to highlight it, that for unit step system, if your system is type 0, error is going to be 1 by 1 plus kp. If your system is 1, error is going to be 0. If your system type is 2, error is going to be 0. So, if you keep on increasing the odd type of the system for unit step system, the error is becoming 0. So, error is becoming 0 is desirable. Okay, that is why this part is clear. Now, consider unit ramp input. Unit ramp input happen, the error is this unit ramp input means you have to solve 1 by s square, g of shs entire thing. Now, look at for type 0 system. If you solve it, this quantity is going to be 0 and the error is going to be infinite, and this is going to be 1 by kv and this is going to be 0. So, this information you can fill up if you solve it. The error which I have mentioned, this part for this input, and if you have a unit parabola, then your this point error is going to be infinite 1 by Ka. So, because of the lack of time, I am not going in inside detail. You can solve it the way I have done. So, from there we can to conclude that if I am increasing the type of the system for unit step, the error is coming down. Okay, can you see? For the unit ramp input, look at error is infinite, not at all desirable. But this error is 1 by kV, error is 0. So, if you are increasing the type of the system, error is coming down. For unit parabola, type 0 system, infinite error. System, infinite error. Type 2 system, 1 by k, it has come down. So, one conclusion we want to make it here, if you increase the type of the system, the error will come down. Okay, this is the important message you should keep in your mind. Okay, so this is what I want to convey. Okay, this is the diagram which I have given you your home hands out. Please look at it, and it's very straightforward. You can work it out. But from this, you can conclude that if I increase the type of the system, the steady state error is going to. So, what we have studied till now, that what we have studied, dynamic response of the system, then we consider first order system, second order system, and then we went for the how to quantify the first order system, second order system, and then peak time, settling time, rise time, maximum overshoot, how we can compute the value, how it is behaving it, what is desirable in a first order system, second order system. Then we went for we solve a numerical problem. I want you to go back and see, you still all of you can solve. And the last, I just explained the error constant, which I have explained you the steady state error. Okay. Now next I wanted to explain the different controller, because this is what the objective of this module is, that you should, the objective of this module is to understand or to see the behavior of the objective of the behavior of the system is to look at the dynamic of the response of the system, how is it behaving under the influence of different controller. Okay. So for that, if you remember, come back to the again this part, E of S, A of S, E of S, how is it coming? Okay, H of S. Okay, this is what has happened. And what should be this D of S? This is, I talk about it, different controller we use it. Okay, so the three types of controller are very popular. One is a proportional controller, another is a integral controller, and third is a derivative controller. Okay, so this we use P, I, D. Okay, only proportional controller, integral controller, derivative controller. Then we use combination of these P, PI, PID. Okay, so these three controller we will be plugging it, and we will be analyzing the system response YT for a different input. And to analyze it means we will be quantifying, and the quantifying parameter is going to be like your peak time, settling time, rise time, overshoot, steady state error, steady state value, all these things will be looking at. So at this point I want to stop it, and tomorrow we will be looking at the this different controller and how does it behave. Thank you. Thank you very much. Hello MCKB.
Hello, sir.
Is that
Hello,
fine?
sir.
Can you respond from
What?
there? Yeah, so I am just
Yeah, sir.
whether you were able to follow what I have explained. Hello
Yes.
MCKV. Hello MCKV.
Hello,
Yeah.
sir. What is the situation when the graph will move to the steady state in K versus T plot?
Sorry, what will the, I missed your question. Can you repeat?
What is the situation when the graph will move to the steady state in K versus T plot?
Yeah, steady state means it will reach to a unity whatever steady state value. So what is the exact question in that?
Sir, what is the situation when the graph will move to the steady state condition in K versus T plot?
Graph will reach steady state. So what is your y axis? What is your x axis?
In YK and in XT.
Okay, if you look at the steady state response, you mean to say how is it going to behave like this? It will reach to this value. As t tend to infinity, it will reach to the steady state value 1, your response. This is your second order system, and this is where it will go, and finally it will reach to this value. And for a unit step input, this is going to be 1.
Yes, sir. Sir, another question is there.
Yeah.
Physical significance of zeta.
Zeta. Zeta is your damping factor, and okay, physical significance. I would say it depends on the which domain I am applying. If I am using a mechanical system, this is equivalent to your elasticity B, viscous friction constant with no friction. Okay. So if I am going an electrical circuit, it is going to be some combination of RLC. Okay. So it is not easy to define the physical significance unless I know the domain which I am applying. I know only that zeta is 0, then how is it behaving it. To relate it to some specific physical, I should know which application I am applying, and the application where I am using the mechanical system or electrical system, it should depend on that. So that's why we can't generalize it that.
Okay, sir. Now one question, uh, how we define zeta? How we define zeta?
As I explained, zeta is a damping factor. If you look at the quadratic equation, s square plus 2 zeta omega ns plus omega n square, and that is where the zeta has come. And the damping factor, the way it is coming, the way you are damping your response. Damp means it is coming down.
Okay, sir. Thank you.
Root locus of second order system. Since I have not covered a root locus plot, but root locus plot itself is required some time, and I can explain you. And you can do it in this, as I explained, the way two roots are moving it, that's going to be locus. I can cover it tomorrow for some time.
Sir, hello. Hello.
Yes.
Sir, what is the range of zeta we can select for achieving a better performance?
It is generally suggested 0.5 to 0.7. Typically,
Thank you.
most of the zeta ratio should vary from 0.4 to 0.7. It is desired. This is the range we use it, and we know that there is an extreme scenario in which how does it behave, but it is the most of experimental value. We can't say in well advance that is the value you should be using it. Take sign up. You can write a question. We will take it. Thank you.